Turn your shower to cold, not all the way, just enough that the water bites a little against your chest. Hold it there for 10 seconds and pay attention, really pay attention, to what happens to your hands. They go pale. The color drains from the fingernails first, then from the knuckles, then from the pads of each finger, moving inward like a tide pulling back from shore. You are watching your blood leave, in real time. Right there in your own shower, you are watching a rerouting event that involves more coordinated engineering than anything we have ever built in a laboratory. And I want to walk you through exactly what is happening inside the walls of those blood vessels, because the physics of it is absolutely worth your time. Now, your skin. It is threaded with roughly 100,000 kilometers of blood vessels. I want you to think about that number. 100,000 kilometers. If you could pull them all out and lay them end to end, that network would wrap around the Earth 2.5 times. Most of those vessels are capillaries, tiny things, so narrow that a red blood cell has to actually deform, fold itself nearly in half, just to squeeze through single file. But buried in the skin of your fingertips, your earlobes, the soles of your feet, the bridge of your nose, there are structures that most people have never heard of, and they are the key to everything I am about to tell you. They are called arteriovenous anastomoses. Now that is a mouthful, but the word just means connection between artery and vein. These are short-circuit vessels, direct tunnels. They bypass the capillary bed entirely, they skip the whole business of gas exchange and nutrient delivery, and they connect your arterioles straight to your venules. Nothing but a high-speed conduit for blood. And each one is wrapped in a thick ring of smooth muscle that can open or close in milliseconds. When these rings relax, blood floods the skin surface, and you radiate heat like a furnace with the vents thrown wide. When they contract, the blood retreats to the core, and the skin goes cold. These are not passive pipes. They are valves. Thousands of them in the fingertips and toes and lips and ears, all under the direct real-time control of the sympathetic nervous system. The same system that runs your fight-or-flight response is right now, this second, adjusting the diameter of blood vessels in your smallest finger without asking your permission. It does not need your permission. The system runs on its own. And I want you to appreciate the control problem here, because it is a serious one. The body has to regulate heat loss across a surface that changes temperature depending on which room you walk into, which sleeve you roll up, which breeze hits your neck. It is doing this across 100,000 kilometers of plumbing, with thousands of independently controlled valves in real time continuously while you think about what to have for lunch. The computational load for this regulation alone, if you tried to replicate it in silicon, would be substantial. Your body does it without a single conscious thought. Now, when warm water hits your skin, these anastomoses stay relaxed, blood flows freely, and the body sheds heat through the skin surface. A warm shower is pleasant, sure, but from a physiological standpoint, it is your cardiovascular system in idle, coasting, the vascular equivalent of lying on a couch. The cold water changes the entire conversation. When cold hits the skin, the first thing that happens is not cardiovascular, it is electrical. Temperature-sensitive nerve endings, thermoreceptors, fire a volley of signals through A-delta fibers, the fast myelinated fibers that carry sharp sensation, traveling at about 15 meters per second up to the spinal cord and then to the hypothalamus. That is the thermoregulatory command center at the base of your brain, smaller than an almond, responsible for temperature regulation in every square centimeter of your body, and the hypothalamus does not think it over. Within about 200 milliseconds, it fires a command down the sympathetic chain. Nerve terminals embedded right in the walls of your blood vessels dump norepinephrine, also called noradrenaline. This molecule is the primary driver of cold-induced vasoconstriction. It binds the alpha-1 and alpha-2 adrenergic receptors on the smooth muscle and tells them to contract. It accounts for roughly 60% of the reflex constriction in the skin vasculature. Another 20 to 30% comes from a co-transmitter, neuropeptide Y, released from the same terminals in the same volley. But here is the thing that makes the physics interesting. There is a second mechanism operating at the same time, and this one does not involve the brain at all. The smooth muscle cells in the vessel wall are cooling directly, locally, and that local cooling activates an intracellular enzyme called Rho kinase. Now, Rho kinase does two things at once, and both of them push in the same direction. First, it inhibits myosin light chain phosphatase, the enzyme that would normally let the muscle relax. With the phosphatase blocked, the contraction locks. The muscle cannot unclench. Second, Rho kinase causes alpha-2C adrenergic receptors to physically move from the Golgi apparatus inside the cell to the plasma membrane on the surface. Receptors that were in storage get pushed to the front line. So now you have more receptors exposed, and the smooth muscle becomes dramatically more sensitive to the norepinephrine that is already pouring in from the sympathetic discharge. The vessel is being squeezed from two directions at once. The brain is commanding it to close from above. The local tissue is making it chemically easier to stay closed from within. And the result is vasoconstriction so fast and so complete that blood flow to the skin of your fingers drops by more than 90% in under 60 seconds. That is the first mechanism. It is not the one that matters most. What happens next is the part that a Welsh cardiologist named Thomas Lewis first described in 1930, and it is, I think, one of the more beautiful things in all of physiology. Lewis was working at University College Hospital in London, and he stuck a subject's finger into ice water and watched the skin temperature fall. Vasoconstriction. Heat conservation. Standard textbook stuff. Then, after about 5 to 10 minutes, the temperature started going back up. The finger was still in the ice water. Nothing had changed externally. But blood was coming back. The vessels were reopening on their own. Lewis watched the skin flush pink, hold that warmth for a few minutes, then go pale again. Then open again. Then close again. The vessels were oscillating. Constriction, dilation, back and forth in a rhythm that Lewis called the hunting reaction. And the best explanation we have centers on the smooth muscle of those anastomoses. Below about 15 degrees Celsius, the muscle fibers cannot sustain their tone. The contraction fails. The muscle relaxes. Blood rushes through, warms the tissue, and as it warms, the muscle regains its ability to contract, clamps down again, and the whole cycle restarts. Now, this is not a malfunction. This is a negotiation. Two priorities that the body has to balance every second of cold exposure. On one side, conserve core heat by keeping blood away from the skin. On the other, prevent tissue death by periodically letting blood return. If the vasoconstriction were permanent, you would preserve your core temperature, but you would lose your fingers. Ischemia. Oxygen starvation. The hunting reaction is the body's compromise, and it is an elegant one. Think about what this means from an engineering standpoint. The system has to fail gracefully. It cannot simply maximize one variable, because optimizing for core temperature destroys the periphery, and optimizing for peripheral perfusion bleeds all your heat away. So what evolution produced is an oscillator, a system that alternates between two imperfect states, spending enough time in each one to prevent catastrophe in either direction. If you were designing a thermostat for a building with these constraints, you would arrive at the same solution. Alternating modes. Cycling. And if you ran that cycling long enough, the system would get better at it. Now I want you to think about what happens when you repeat this. Not once, not in a laboratory, daily, for weeks. You are forcing the blood vessels through contraction-relaxation cycles under load. The smooth muscle is being challenged to respond, recover, and respond again. Any exercise physiologist will tell you what to call that. Training. Hein Danen at Vrije Universiteit Amsterdam showed this directly. He took 16 young adults and had them immerse one hand and one foot in 8-degree water, 30 minutes a day, 15 consecutive days. The other hand and foot were tested only on day 1 and day 15 as untrained controls. By day 15, the trained foot showed higher toe temperatures during cold immersion, rising from 9.49 degrees to 10.03 degrees. The vasodilation response was getting more efficient. But here is the part that caught my eye. The trained hand showed a decrease in finger temperature. The fingers were getting colder. The vessels were clamping down harder. The reason is geometry. Fingers have a surface area to volume ratio of roughly 104 square meters per meter cubed. Toes sit at about 68. More surface area means faster heat loss, so the finger vasculature was learning to constrict more aggressively to compensate, while the toe vasculature was learning to allow more blood through to protect tissue. The system was not uniformly tightening or loosening. It was optimizing, location by location, based on the thermal geometry of each extremity. The same cold water, same temperature, same duration, producing different vascular adaptations in different parts of the same body. And the evidence for this kind of remodeling goes well beyond the laboratory. The Korean haenyeo, the female freedivers who have harvested shellfish from cold ocean water for generations, were studied by Suk Ki-hong in the 1960s. These women dove year-round into water as cold as 10 degrees Celsius wearing only cotton. Hong measured forearm blood flow at progressively colder water temperatures and found something unexpected. The divers maintained higher blood flow than non-divers at every temperature tested. Their bodies had solved the thermal equation differently. Instead of choosing between heat conservation and tissue protection, the diver's vasculature had learned to do both, maintaining perfusion without losing core temperature. Decades of cold exposure had rewritten the vascular program. The adaptation goes deeper than smooth muscle. When the vessels constrict and then reopen during the hunting reaction, the blood that surges back through creates something the vessel wall detects with great precision: shear stress. The physical friction of blood flowing across the endothelium, the single-cell layer that coats the inside of every blood vessel in your body. If you peeled it out and laid it flat, it would cover 6 tennis courts, 1 cell thick. And it is not a passive lining. It is a sensory organ. It detects flow velocity, direction, pulsatile patterns through mechanosensitive proteins in the membrane, ion channels, integrins, tiny projections called primary cilia that bend in the direction of flow. The endothelium converts mechanical force into chemistry, and the most important molecule it produces is nitric oxide. 1 nitrogen, 1 oxygen, a gas, made by an enzyme called endothelial nitric oxide synthase, which is activated primarily by laminar shear stress, the smooth directional flow of blood along the wall. Kaironisa Binti MD Isa at Kyushu University tested this directly. She cultured endothelial cells under combined shear stress and temperature changes. At body temperature, shear stress increased the activated form of the enzyme by 55% within 15 minutes. At 28 degrees, a mild cooling, the activation climbed to 134.8% of baseline in the same window. So what is happening in your shower is this. Each time the vessels constrict and then reopen, the returning blood creates a shear stress pulse across the endothelium. That pulse activates nitric oxide synthase. The enzyme makes nitric oxide, which diffuses into the smooth muscle and causes relaxation. It also inhibits platelet adhesion and reduces the expression of the adhesion molecules that attract inflammatory cells to the vessel wall, the earliest step in plaque formation. Philip Tsao at Stanford published in Circulation in 1995 that just 30 minutes of laminar flow reduced endothelial adhesiveness for monocytes by 50%. The effect was almost entirely mediated by nitric oxide. Block the enzyme and the protection disappears. Every constriction dilation cycle in your cold shower is a training rep for the endothelium, a set of repetitions that reinforces the enzymatic pathway producing the most protective molecule in the cardiovascular system. and the signal does not stop at the vessel wall. The cold triggers a sympathetic discharge that reaches far beyond the skin. The adrenals release epinephrine. Sympathetic terminals throughout the body release norepinephrine. And the magnitude is not subtle. A study in the Journal of Applied Physiology immersed 6 men in 10-degree water and measured plasma norepinephrine over 60 minutes. Baseline was 359 picograms per milliliter. After 2 minutes, it nearly doubled to 642. By 45 minutes, it peaked at 1,171. A 3.26-fold increase. At milder temperatures with longer durations, the numbers are even larger. An hour at 14 degrees Celsius increased norepinephrine by 530% and dopamine by 250%. Now, norepinephrine is not only a vasoconstrictor. It is the primary activating signal for a tissue that until 2009 most people thought was irrelevant in adult humans. Brown adipose tissue, brown fat. In 2009, 3 papers came out almost simultaneously. Wouter van Marken-Lichtenbelt at Maastricht University published in the New England Journal of Medicine, using the same PET-CT imaging we use to find tumors, and showed that adult humans have active brown fat depots above the collarbones, along the spine, around the kidneys, not vestigial, not left over from infancy, functional, burning glucose, and directly responsive to cold. Brown fat works like this, and the physics here is genuinely interesting. In a normal cell, the mitochondrial electron transport chain builds a proton gradient across the inner membrane, and ATP synthase uses that gradient to make adenosine triphosphate, the universal energy currency. Every biology textbook draws this as a neat diagram. Protons get pumped out, they flow back through the turbine, ATP comes out the other side. Elegant. Efficient. That is how most of your cells make energy. In brown fat there is a protein called uncoupling protein 1 sitting in the same membrane, and it does something that, from an engineering perspective, looks like sabotage. It opens an alternative channel. Protons leak back across without passing through the turbine. No ATP gets made. The gradient dissipates. And all that energy, the chemical potential that would have been stored as usable fuel, comes out as heat instead. Now, why would evolution build a protein whose entire job is to waste energy? Because wasting energy as heat is not waste when you are a mammal that needs to maintain 37 degrees in a cold environment. Brown fat is a dedicated space heater built into your own body. The mitochondria run at full capacity, burning fatty acids, consuming oxygen, producing nothing but warmth. And the density of mitochondria in brown fat cells is so high, packed so tightly with iron-containing cytochromes, that the tissue appears brown under a microscope. That is where the name comes from. The color of the iron. Cold activates this through the same norepinephrine pathway your shower triggers. The norepinephrine hits beta-3 adrenergic receptors on the brown fat cells, breaks down stored triglycerides into free fatty acids, and those fatty acids both fuel the mitochondria and directly activate uncoupling protein 1. The protein cannot open its channel without them. Van Marken-Lichtenbelt's group later showed, in the Journal of Clinical Investigation in 2013, that 10 days of cold acclimation at 15 degrees Celsius significantly increased brown fat activity and recruited new thermogenic cells. And here is where it gets particularly interesting. Some of those new cells were not classical brown fat at all. They were beige adipocytes, cells that had been sitting within white fat depots looking like ordinary storage cells, that began expressing uncoupling protein 1 when exposed to sustained norepinephrine signaling. The body was converting storage tissue into combustion tissue. White fat was turning brown. Not metaphorically, literally. Under the microscope, these cells develop the dense mitochondria and multilocular lipid droplets that characterize brown fat. The line between white fat and brown fat, which the textbooks drew as permanent, turns out to be negotiable. Cold is the negotiator. So the same cold signal that trains your blood vessels and stimulates your endothelium is also expanding your capacity to generate heat from stored fat. One stimulus, multiple systems, all connected through the same norepinephrine pathway. Now I want to be careful here, because I think one of the most important things you can do when you learn about biology is to ask not just what is the mechanism, but how strong is the evidence for each piece of the mechanism. And these pieces do not all sit on the same footing. You deserve to know which ones you can trust fully and which ones require some caution. I will grade them as honestly as I can. The vascular training, the hunting reaction, the adaptation done and measured, that is bedrock physiology. Measured continuously since Lewis in 1930, replicated for 90 years, confirmed in the Korean diver population studies. Solid. The shear stress and nitric oxide mechanism is well established at the cellular level. The in vitro data from Kyushu, the Stanford flow studies, those are clear. What is less certain is the exact dose. The specific shear stress magnitude generated during a domestic cold shower has not been directly measured in human skin microvessels in vivo. The mechanism is physiologically consistent with everything we know. The precise translation to your shower is an inference, not a measurement. Brown fat activation by cold is strong for immersion and climate chamber protocols. PET-CT data from Maastricht, Turku, multiple centers, all consistent. What sits in a lower tier of certainty is how much brown fat activation a brief daily cold shower achieves compared to 6 hours per day in a controlled climate chamber. The shower stimulus is shorter and milder. The norepinephrine response, though, is the most robust finding in the entire literature. Jari Lepeluoto at the University of Oulu in Finland studied women doing winter swimming 3 times per week for 12 weeks. The cortisol response habituated by week 4. But norepinephrine showed 2-fold to 3-fold increases every session for the full 12 weeks. No desensitization. Every time. That is unusual. Most stress hormones attenuate with repeated exposure. This one does not. Now put all of this next to a pharmaceutical shelf. There is a drug called mirabegron, brand name Myrbetriq, approved in 2012 for overactive bladder. It activates beta-3 adrenergic receptors, the same receptor that norepinephrine activates on brown fat cells. Aaron Sipos at Harvard Medical School, later at the National Institutes of Health, showed in Cell Metabolism in 2015 that 200 milligrams of mirabegron activated brown fat in all 12 subjects and increased resting metabolic rate by 203 kilocalories per day, 13%. Same receptor, same cascade, same uncoupling protein, same fat depots. A 1-month supply at the standard 50 milligram dose runs $300 to $400 without insurance. At the 200 milligram dose that matched cold exposure effects, it also raised heart rate and blood pressure, because at that concentration the drug binds beta-1 receptors in the heart. An off-target effect. Cold water hits the same target without the cardiac side effect. And it simultaneously generates the vascular training, the endothelial shear stress, the full norepinephrine cascade, and the dopamine surge. The drug isolates one pathway. The cold water pulls the whole system at once. But I want to be honest about the dose. A 60-second cold shower does not produce the same norepinephrine surge as an hour at 14 degrees. The brown fat activation from a brief shower is real but modest. Mirabegron exists for good reason, because many people cannot tolerate cold, and for certain clinical populations, a targeted drug has genuine value. The point is not that the drug is unnecessary. The point is that the pathway it targets was already built into your body, available at no cost, activated by a stimulus your species has encountered every single day for 200,000 years. Think of the person who is 67. Whose blood pressure has been creeping up for the last 5 years, 2 or 3 points per annual visit, a slope so gentle that each individual reading is dismissed as normal variation, but the trend line tells a different story. whose statin dose was raised last year, whose mornings start with 8 minutes of hot water, because the heat feels good on stiff joints, and the idea of voluntarily standing under cold water seems like something only a 25-year-old would do. That person's endothelium is making less nitric oxide every year, measurably less. The smooth muscle in their arterial walls is stiffening with each passing decade, losing the ability to dilate fully, which is one of the primary drivers of age-related blood pressure increase. Not plaque, not cholesterol, stiffness, the pipe getting rigid. Their brown fat depots, which were active and visible on PET scans in their 30s and 40s, have been quietly shrinking, replaced by white fat that stores calories instead of burning them. Their sympathetic nervous system still fires in response to cold, but the downstream tissues respond with less vigor, a phenomenon called age-related autonomic blunting. And their thermostat-controlled home, maintained between 20 and 22 degrees year-round, has eliminated the very stimulus that human physiology evolved to expect. Van Marken-Lichtenbeldt's group found that mean arterial pressure at rest was lower after cold acclimation, even in warm conditions. The body was not just enduring cold better. Its baseline cardiovascular parameters were improving. A cold shower will not replace a blood pressure medication. It will not substitute for exercise or a better diet. Those interventions have decades of clinical trial evidence behind them, but it will do something no pill in their cabinet does. It generates a simultaneous training pulse across the vascular smooth muscle, the endothelium, the sympathetic axis, and the thermogenic fat tissue. 30 seconds, every day. The vessels practice contracting and relaxing. The endothelium practices making nitric oxide. The brown fat practices burning fuel. The autonomic system practices firing and recovering. The discomfort is not an obstacle. It is the training stimulus. Now here is the last thing, and it is the part I like the most. Someone in your family, your grandmother, your mother, maybe a coach or a village doctor from 50 years ago, had a phrase for this: a cold shower will toughen you up. She did not know about endothelial nitric oxide synthase. She did not know about uncoupling protein 1 or Rho kinase translocating receptors to the cell surface, or Thomas Lewis watching blood vessels oscillate in ice water in 1930. She did not know that norepinephrine rises threefold and keeps rising, session after session, for 12 weeks without fading. She just knew it worked. The molecular explanation took another century to catch up. Turn the dial. 30 seconds is enough. Feel the cold hit your chest. Feel your hands go pale. Feel the vessels close. Wait. Feel them open. Now, I want to hear from you. What is one thing your body does automatically every day that you suspect has more physics behind it than anyone has bothered to explain to you?